Hello everyone, myself Arunkumar Kannan from Biomedical Signal and Image Computing Laboratory at the University of British Columbia will be presenting our paper on uncertainty estimation for assessment of 3D ultrasound scan adequacy and DDH metric reliability. Developmental dysplasia of the hip is one of the most common congenital disorders affecting the newborns. It is a condition that is characterized by hip joint instability, in which the femoral head will be slightly dislocated from the bone socket that leads to trouble in walking and other problems like limping, leg length discrepancy, and pain at the later stage of life. Current clinical practice for DDH diagnosis relies completely on 2D ultrasound imaging of the newborn hip. Quadr et al. Reported 2D ultrasound to have significant variability, which motivated the exploration of 3D ultrasound to diagnose DDH. They further extracted hand-engineered features from 3D ultrasound to segment the femoral head, ilium, and acetabulum regions. Later, Hariri et al. Used deep-learned features to localize the same bony regions and reported that deep learned features perform better than the hand-engineered features. Despite these significant contributions, several limitations remain, the most important of which is the model opacity of the neural network. As deep neural network becomes a part of the clinical workflow, it presents generalizability and interpretability problems. Hence, we propose an interpretable uncertainty measure that can quantify a unit-like architecture's reliability. In addition, our proposed measure also helps in automatic assessment of adequacy. We use a 3D unit architecture for segmenting the bone surfaces. We feed forward a 3D ultrasound volume to the unit architecture. We use Gall et al.'s approach of predicting the model uncertainty by enabling dropout at test time to generate the Monte Carlo sample. We extract the suitable DDH metrics like 3D alpha and 3D femoral head coverage from the segmented Monte Carlo samples to calculate our uncertainty measure. We propose our uncertainty measure in DDH metric as a standard deviation, in which n denotes number of Monte Carlo samples, yn is the DDH metric extracted from each of the Monte Carlo sample, and y is the average of the metric. We further calculate structure-wise uncertainty measure similar to Roy et al. To evaluate our proposed metric. It is calculated as the pairwise dice combination of each of the Monte Carlo sample. We present our qualitative findings here. The images represent 3D scans acquired from different participants. An expert radiologist labeled the volume as yes, denoting that all adequate structures are present in our proposed uncertainty metric. Circular region represents the femoral head, and the curved line represents the ilium and acetabulum surfaces. The different colors overlaid on each other represent the segmented Monte Carlo sample. Our proposed uncertainty metric was able to quantitatively report our scan adequacy because the adequacy label with yes has low uncertainty. Contrast, in case of inadequate cases where the insufficient structures are not there, uncertainty measure is high as expected. This confirms the fact that accurate and robust ultrasound volume is required for diagnosing DDH. We conclude our findings by reporting that our proposed uncertainty measure can be augmented in deep learning framework for DDH assessment. The proposed measure helps in quantifying the network's reliability, and it can also classify the adequacy or inadequacy of ultrasound scan. Our future work focuses on assessing our model's generalizability to ultrasound data collected at multi-institutional pediatric orthopedic centers. I would like to personally thank my supervisor and collaborators for their constant encouragement and support. I would also extend my thanks to the funding resources like UNSURE, NVIDIA, and Compute Canada for supporting our research. Thank you.